Physical movement often follows predictable, continuous curves, from the arc of a fountain to a steel ball launched into the air. When we freeze a structural curve in place, like the suspension cables on this bridge, we can trace its path with mathematical precision. Polynomials provide the exact mathematical language required to replicate and predict these trajectories in abstract space. This language is built from three components: constants, variables, and exponents that define the power of those variables. Operating within the translation layer allows us to convert these abstract numbers directly into physical geometric shapes. This conversion is essential for engineers, as it allows them to model continuous real-world motion on paper before construction begins. For an expression to qualify as a polynomial, the exponents must be non-negative integers, whole numbers like 0, 1, 2, and 3. Using whole numbers like 3x squared ensures a smooth, continuous curve. An exponent of 1/2 introduces a square root, undefined for negative x, making the graph vanish. And negative power involves division by 0, forcing the graph to shoot to infinity and break apart. Because physical mass cannot vanish from one coordinate and reappear in another, or become infinite at a single point, these undefined zones break the mathematical model of physical space. Restricting exponents to 0 and positive integers prevents these mathematical glitches, guaranteeing the unbroken lines needed to represent physical reality. This specific constraint makes polynomials a reliable tool for simulating how objects move through the physical universe. We organize this tool using a standard general form, which lists the variable x, the coefficients, and a leading coefficient that determines the start of the expression. The highest exponent in the expression is the degree of the polynomial. This degree acts as the architect of the curve, dictating the fundamental geometric shape the equation will trace. A degree 1 polynomial is linear, producing a perfectly straight line. A degree 2 polynomial is quadratic, which always forms a parabolic curve. A degree 3 cubic polynomial creates an S-curve, a shape used to design smooth transitions in architectural splines. Identifying the highest exponent allows us to predict the physical shape of a curve before plotting a single coordinate point. We anchor these shapes using zeros. In algebra, a zero is any real number that, when plugged into the equation, makes the entire result equal 0. This chart shows the geometric reality of a zero on a Cartesian plane. Look at point A. Geometrically, the 0 is the exact x-coordinate where the graph pierces the horizontal x-axis. The fundamental theorem of algebra states that a polynomial of degree n can have at most n real zeros, meaning a quadratic curve can cross this axis a maximum of 2 times. Finding these zeros identifies the exact physical coordinates where a moving object hits the ground level of our coordinate system. Quadratics follow this rule strictly. A degree 2 parabola interacts with the ground axis in exactly 3 ways. In case 1, the parabola crosses the x-axis at 2 distinct points, creating 2 real zeros. This represents a physical projectile in motion, like a soccer ball, launching from the ground and landing further down the field. In case 2, the parabola touches the x-axis exactly once, where the 2 zeros coincide, representing an object grazing a surface. In case 3, the parabola floats entirely above the axis. With no real zeros, it represents an object that never hits the ground. These 3 cases provide a framework for calculating exactly when and if a moving object will reach its boundary. The points where a curve hits the ground are not random. They are strictly controlled by the algebraic structure of the equation. These geometric roots, alpha and beta, are mathematically hardwired to coefficients a, b, and c. 2 symmetric rules govern this. The sum of the roots always equals the ratio of b divided by a. Additionally, their product equals c divided by a. This relationship allows us to build an algebraic equation directly from geometric observations. Using the master formula, we can take the observed sum and product of the endpoints and drop them directly into a standard equation format to generate the curve. If an engineer knows where a bridge must anchor to the earth, they can use this symmetry to reverse engineer the exact mathematical arch required to connect those points. Those symmetric functions remain unchanged even if the values of the two roots are swapped. This bridge allows us to calculate complex geometric relationships, like the squares of the distances between roots, purely through algebraic substitution. Manipulating these coefficients is the underlying engine that converts raw numbers into physical space. A polynomial equation functions as a physical replica of reality. The algebraic variables written on the page and the physical structure are simply two different ways of expressing the exact same mathematical truth. By mastering these relationships, we gain the ability to translate abstract calculations into the precise physical structures that define our world.